So we can come back to the original equation, the differential equation describing this interaction. Now, to solve this equation, you think about the total amount of TLR, and the total amount of TLR will be composed of inactive TLR plus active TLR. Let's just write the total amount of TLR as TLR, and this will be a constant. There's a limited amount of TLR. It can be either active or inactive, depending on the presence of the LPS. But the absolute amount of TLR will be constant in a given amount of time that we are considering. So we can rearrange the equations after inserting this into this. Needless to say, we can write inactive TLR as TLR minus active TLR. Now TLR is constant once again, so we are essentially considering active TLR only. The reason why we are only considering active TLR is because we are considering the differentiation of active TLR over time. So we can rewrite the equation like this. But then we can put the active TLR together. So this is just a basic algebra. What we do is, using the distribution, F multiplied by LPS will be distributed into two terms. So we get to have these two terms. And then these two terms can be now combined with active TLR. So we'll have one term over here and the other term with active TLR, which is multiplied by F LPS plus R. Now, if you want to manipulate a little bit further, you can take out the F. Then you'd have to divide R with F, and you get to have this. And now, R of F is KD. So finally, you get to arrive at this equation. Let's think about this equation. So we already discussed how to solve this in our previous discussion in week 2 with an analogy of leaky water tank, which is composed of an in rate. Now the in rate is constant, just like the leaky water tank. And also, there is an out rate multiplied by minus sign, and this is proportional to the active TLR itself. And multiplied by that is just a constant. So basically the format we have is just the same as what we had before. Some in rate constant minus some constant multiplied by itself. So you know the solution to this already. As we have discussed, in such case, it is bound to have a steady state. So over time, when time goes to infinity, it will reach some level and it will not change forever. It begins from some initial condition. To be practical, almost all TLR will be inactive when there is no LPS. So you can actually bring it down to 0. But just to be general, we can consider that there can be some kind of TLR at time 0. Now, as you have already seen, TLR is composed of active TLR and inactive TLR. So the total amount of TLR will be conserved. This is constant. Basically, inactive TLR will be TLR minus active TLR. So we'll have this kind of relationship. Or you can rewrite the whole equation, not in terms of the active TLR, but in terms of inactive TLR, and get to the same conclusion. Just to make sure, you can put these little cubes of the same height at certain point of time, here and here, and here and here. And then we can rearrange just to make sure that they actually do conserve. Now we want to think about the active TLR dynamics. Once again, we consider the steady state. That means that d active TLR over dt is 0. And once again, you take this part to the left-hand side. And notice that when there's no change in the rate, this active TLR will actually be the steady state TLR. So you write like that with the infinity sign. And then divide the right-hand side with f multiplied by LPS minus KD to get the steady state active TLR, which is LPS TLR divided by LPS minus KD, which has a functional form like this. This is quite interesting. KD comes in. And LPS can be a variable because there can be different amount of LPS given. But TLR is a constant. But it can also reflect the state of the cell. Sometimes there will be more TLR receptors expressed, sometimes not. So this gives you an idea of the maximum of active TLR. And all of this will depend on KD. Suppose LPS, amount of LPS, is exactly KD, which is, as you know, about nanomolar range. Then in that case, active TLR in the steady state will be TLR divided by 1 plus KD over KD, which cancels out to be just 1 and will be just TLR divided by 2. What does it mean? When LPS has a concentration same as the dissociation constant, it will indicate the half maximal concentration. If LPS is available in the concentration range lower than KD, then the change will be approximately linear. And it goes above the KD, it starts to saturate. If LPS is available in a concentration much larger than the KD, it will almost always activate TLR to the saturating range.